This is the first two papers beyond the analogos of the great Hypersigil. And with these two papers, we really establish it is what it is.
New proof reveals fundamental limits of scientific knowledge. A new proof by SFI. Professor David Wolpert sends a humbling message to would-be superintelligences. You can't know everything all the time. The proof starts by mathematically formalizing the way an inference device, say a scientist armed with a supercomputer, fabulous experimental equipment, etc., can have knowledge about the state of the universe around them. Whether that scientist's knowledge is acquired by observing their universe, controlling it, predicting what will happen next, or inferring what happened in the past. There's a mathematical structure that restricts that knowledge. The key is that the inference device, their knowledge, and the physical variable that they may know something about are all subsystems of the same universe. That coupling restricts what the device can know. In particular, Wolpert proves that there's always something that the inference device cannot predict, and something that they cannot remember, and something that they cannot observe. In some ways, this formalism can be viewed as many different extensions of Donald McKay's statement that a prediction concerning the narrator's future cannot account for the effect of the narrator's learning that prediction. Wolpert explains, perhaps the simplest extension is that when we formalize inference devices mathematically, we notice that the same impossibility results that hold for predictions of the future McKay's concern also hold for memories of the past. Time is an arbitrary variable. It plays no role in terms of differing states of the universe. Not everyone can be right. What happens if we don't require that an inference device know everything about their universe, but only that it knows the most that could be known? Wolpert's mathematical framework shows that no two inference devices who both have free will appropriately defined and have maximal knowledge about the universe can coexist in that universe. There may or not be one such super-inference device in some given universe, but no more than one. Wolpert jokingly refers to this result as the monotheism theorem, since while it does not forbid there being a deity in our universe, it forbids there being more than one. As an example, suppose that Bob and Alice are both scientists with unlimited computational abilities. Moreover, suppose that they both have free will, in that the question Bob asks himself does not restrict the possible questions Alice could ask herself, and vice versa. This turns out to be crucial. Then it is impossible for Bob to predict or retrodict what Alice thinks at another time, if Alice is also asked to predict what Bob is not thinking at that time. Wolpert compares this proposition to the Cretan liar's paradox, in which Epimenides of Knossos, a Cretan, famously stated all Cretans are liars. The unlike Epimenides statement, though, which exposes the problem of systems that have the capability of self-reference. Wolpert's reasoning also applies to inference devices without that capability. In addition, in Wolpert's formalism, the same scientists, considered at two different moments in time, is two different inference devices. So while it could be that's an inference device is a super inference device at one moment, they could not be so more than once. Again, tongue-in-cheek, he refers to this as the deism theorem, since it allows there to be a deity that knows the most that could be known at the beginning of the universe, but forbids there ever being so knowledgeable again, because it does not rely on specific theories of physical reality, like quantum mechanics or relativity. The new proof presents a broad set of limits for exploring the nature of scientific knowledge. None of these results, limiting knowledge acquired by prediction, relies on there being chaotic processes in the universe. It doesn't matter what the laws of physics are, or if Alice is more computationally powerful than a Turing machine, says Wolpert. All of this is independent of that, and it's much broader ranging. This research is progressing in many different directions, ranging from epistemic logic to a theory of Turing machines. In particular, Wolpert and his colleagues are creating a more nuanced, probabilistic framework that will allow them to explore not only the limits of absolutely correct knowledge, but also what happens when the inference devices are not required to know with 100% accuracy. What if Epimenides had said, the probability that a Cretan is a liar is greater than X%, moving from impossibility to probability could tell us whether knowing one thing with greater certainty inherently limits the ability to know another thing. According to Wolpert, we are getting some very intriguing results.
And some of those results apply to our physical world and what it's really capable of. Wow.
Quantum physics problem proved unsolvable. Gödel and Turing enter quantum physics. A mathematical problem underlying fundamental Questions in particle and quantum physics is provably unsolvable, according to scientists at UCL, Universidad Complutense de Madrid, ICMAT, and Technical University of Munich. It is the first major problem in physics for which such a fundamental limitation could be proven. The findings are important because they show that even a perfect and complete description of the microscopic properties of a material is not enough to predict its macroscopic behavior. A small spectral gap, the energy needed to transfer an electron from a low-energy state to an excited state, is the central property of semiconductors. In a similar way, the spectral gap plays an important role for many other materials. When this energy becomes very small, i.e., the spectral gap closes, it becomes possible for the material to transition to a completely different state. An example of this is when a material becomes superconducting. Mathematically extrapolating from a microscopic description of a material to the bulk solid is considered one of the key tools in the search for materials exhibiting superconductivity at ambient temperatures or other desirable properties. A study published today in Nature, however, shows crucial limits to this approach. Using sophisticated mathematics, the authors proved that, even with a complete microscopic description of a quantum material, determining whether it has a spectral gap is, in fact, an undecidable question. Alan Turing is famous for his role in cracking the Enigma code, said co-author Dr. Toby Cubitt from UCL Computer Science. But amongst mathematicians and computer scientists, he's even more famous for proving that certain mathematical questions are undecidable. They are neither true nor false, but are beyond the reach of mathematics. What we've shown is that the spectral gap is one of these undecidable problems. This means a general method to determine whether matter, described by quantum mechanics, has a spectral gap or not, cannot exist, which limits the extent to which we can predict the behavior of quantum materials and potentially even fundamental particle physics. $1 million to win. The most famous problem concerning spectral gaps is whether the theory governing the fundamental particles of matter itself, the standard model of particle physics, has a spectral gap. The Young-Mills mass gap conjecture, particle physics experiments such as CERN, and numerical calculations on supercomputers suggest that there is a spectral gap. Although there is a $1 million prize at stake from the Clay Mathematics Institute for whoever can, no one has yet succeeded in proving this. Mathematically, from the equations of the standard model, Dr. Cubitt added, it's possible for particular cases of a problem to be solvable, even when the general problem is undecidable, so someone may yet win the coveted $1 million prize. But our results do raise the prospect that some of these big open problems in theoretical physics could be provably unsolvable. We knew about the possibility of problems that are undecidable in principle since the works of Turing and Gödel in the 1930s, added co-author Professor Michael Wolff from Technical University of Munich. So far, however, this only concerned the very abstract corners of theoretical computer science and mathematical logic. No one had seriously contemplated this as a possibility, right in the heart of theoretical physics before, but our results change this picture. From a more philosophical perspective, they also challenge the reductionists' point of view, as the insurmountable difficulty lies precisely in the derivation of macroscopic properties from a microscopic description. Not all bad news, co-author Professor David Perez Garcia from Universidad Complutense de Madrid and ICMAT said, it's not all bad news, no. The reason this problem is impossible to solve in general is because models at this level exhibit extremely bizarre behavior that essentially defeats any attempt to analyze them. But this bizarre behavior also predicts some new and very weird physics that hasn't been seen before. For example, our results show that adding even a single particle to a lump of matter, however large, could in principle dramatically change properties. New physics like this is often later exploited in technology, and already is by nature. The researchers are now seeing whether their findings extend beyond the artificial mathematical models produced by their calculations to more realistic quantum materials that could be realized in the laboratory, and more importantly, in our lives.
Now, the information contained in these first two papers is beyond anything that you can find within the hypersigil itself. But please be rest assured that the hypersigil does represent very real, embodied, embedded experience in this real world. To exist is to power set. And you can trust this little hypersigil, it exists too. Il y a beaucoup de bon temps dans la Sud Louisiane. Hey!